Okay, so good morning. And so first of all, I wanted to give a plan and somehow an idea of what the course will be about. First, some organizational detail. So we will meet, these are the meeting times. So this Monday, then Tuesday and Thursday, and then next Monday and next Thursday, okay? And yeah, so the time will be between 10 and 12 and 14, 16. Maybe, I think we can even start at 10 sharp and then see how does it goes. Maybe we will end a bit before, I'm not sure. I'm going to talk for 2 hours, but either we have a pause in the middle or we end a bit earlier. And then again from 2 to 4, and let's agree that we start sharp, okay? If there is no strong recommendation on your side. Okay, so that's the organization. So lecture will be recorded and made available to the participant. What else? Yeah, I have set up a maybe you, if you're here, I think you already found the web page, but I have set up a web page for the course, which is here. So let me copy it here, web page. Yeah, the web page is this one. Okay, I copy in the chat so that maybe you can, where is the chat here? I don't see the chat anymore. I don't know why. Yeah, okay, so this is, I copied in the chat. And there you can find, I will put online the notes of the lecture, and you find a small introduction and some bibliography, okay? Okay, so far for the organizational notes, that's fine. The plan, so let's discuss the plan of the lecture. What I'm planning to do. So yeah, somehow the idea was to discuss some recent result about stochastic quantization of certain quantum field theories, Euclidean quantum field theories. But setting up this course, I thought that actually would be interesting for me, and maybe certainly for me, and maybe also for you to review why we are doing that. So somehow I wanted to give a meaning of all the word appearing in the title. Okay, so there is stochastic quantization. Okay, so we want to give a meaning to quantization, stochastic. Okay, quantization, stochastic. Sorry, quantization. Yeah. Let me say I decided to use the English, the American. Stochastic quantization, Euclidean quantum field theory. Okay. Okay, maybe quantization include quantum field theory, whatever. Okay, so this is ambitious goal, so I will not be able to fulfill it in any reasonable way, but somehow I think interesting intellectually and mathematically to give a look at what are the ideas and the tool involved in going from the problem you want to solve, this is the problem of constructing model of quantum field theories, which is a particular model of quantum mechanical systems in a mathematical language. So trying to be not as precise as possible because we don't have the time maybe, but to introduce the right concept which allow of the correct formalization, okay, which allow to have a rigorous result. and for which rigorous results are available. And then, so yeah, sorry, the conceptual order is actually this one, okay? So there is a problem. This is the problem of quantum mechanics and the quantization of system which have special relativity inside. And then this problem can be solved via a mathematical tool, which is Euclidean quantum field theory, which I try to give an idea about it. And then I want to explain this. Somehow this would be like the core of the novelty of this course is how you do it. So how you construct all the objects you need using this idea of stochastic quantization, which I will try to explain. Okay, so these are the three basic objects, and somehow the lecture will be structured along these lines. Okay, probably maybe the first 2 days, so today and tomorrow, we're going to handle this part, and then from Thursday, we start to speak more precisely on stochastic quantization. Okay, that should be the rough calendar. Okay, and so let me be a bit more precise. Maybe I speak 15 minutes on the plan, and then maybe if you have question or remarks about it. So yeah, so we will start from quantum mechanics. Okay, this is I want to give a basic framework what we understand here in this course by quantum mechanics. And somehow we will talk about so we will talk about the following objects. So sometimes I just copy and paste from my notes, so don't try to write everything. Maybe I will give, this will be a script which will be available at the end of this lecture, okay, as soon as I upload on the web page of the course. So yeah, I want to introduce these concepts, okay? So this will be maybe today and tomorrow. So quantum mechanics, we want to formulate quantum mechanics in terms of an algebra of observables and then states on this observable, that is a way of obtaining number from the things you want to observe. And then we discuss how time enter into this picture, so the dynamics of quantum system. Okay, quantum mechanics is a mechanics, that is you try to describe the motion of certain objects. And then we introduce this idea that somehow this problem, so the problem of quantum mechanics, is in general difficult to solve because it's a non-commutative problem, and there have been devised way to do it in an unexpected by recurring unexpectedly to probability theory. Okay, so there is a connection which I will try to lay out in the broad lines between probability theory and quantum mechanics. And this connection is not the fact that quantum mechanical measurement is probabilistic. That would not enter in our lecture, actually, and we never talk about quantum mechanical measurement. So if you don't know what it is, it's good. If you know, it will not be necessary. But somehow, yeah, this probabilistic connection go through an idea which I find beautiful, which is this idea of reflection positivity. Okay, this is a key idea which somehow I want to advertise in this beginning. It's not very well known, but somehow I find very interesting, and maybe it has other application in your own field of interest. Okay, it's an abstract mathematical tool. Okay, somehow, but this transform what is a quantum mechanical problem into a probabilistic problem. So that's the interest for us, and then we will give example of situation where you have this property, and then we'll discuss a bit what happens for Gaussian and Markov process. And yeah, okay, so you need all these concepts. If you know, it's fine. If you don't know, I mean, if you know, they talk to you maybe, and so they make you interested in the lecture or not interested in the lecture, whatever. If you don't know, it's not important. Okay, I don't assume any previous knowledge. Actually, if you are lost at some point because maybe I didn't really comply with this with this idea, please stop me and ask a question. Okay, this is somehow taught as a lecture for a general public of a graduate student, so I don't assume any okay, not any. Okay, I don't assume. Maybe I will. I think I will use a bit of stochastic calculus at some point. So if you don't know, you have just to trust me that it works as I say. If you know, it will help you. But I try really to minimize. Okay, essentially we will use some analysis and some probability theory, but like concepts of measures, things like this. Okay. Of course, I mean, these topics are quite advanced, so we will not be able to fill all the gaps. Okay, but at least at the beginning, I want to do this overview. So this is an overview, and then at that point, somehow we can. So here we are at a point where we can introduce what is a Euclidean quantum field theory. Okay, and yeah, and then this introduce some problems. So this is like quantum mechanics with infinitely many. So this introduce a problem of dealing with. We will have to deal with probabilistic of infinitely many random variables. Okay, meaning essentially random variable in spaces of distribution and things like that. Okay, not just very simple random variables. And okay, here I think yeah, let me say yeah, I think this is already, if you want, this is part of this Euclidean quantum field theory stuff. And this somehow this is the motivational part. Okay, so we have to deal. So we introduce the two basic problem in this business, which is infinite volume limit and presence of irregular objects on small scale, of objects which are irregular, let's say, of objects which are irregular on small scale. Okay, so this is somehow this is the motivation. Okay, so and we are forced to deal with a certain class of problem because of this initial part of the course. So that's why I wanted to give this motivation. And this introduces a mathematical problem. Okay, we will need to prove existence of certain limits, and that's somehow the central problem in this lecture. So how you prove that this limit exists? Okay, need to prove. We need prove the existence of certain limits, limit objects, if you want, and maybe eventually some of their property. I'm not specific, okay? I just want to give you, I know that maybe it could be even too vague for somebody, but let me, please ask question if you. And how we do this introduces the other idea, which is stochastic quantization. Okay, and stochastic quantization, I will define it really even soon, maybe. And somehow the keywords in this part will be, we will start by studying the Langevin dynamics in finite dimension. So this is somehow, yeah, let me just maybe drop names so far at this moment, because I think just to give a broad outline, okay? And here the problem somehow is that we will have so we will have a dynamic in long time for some object. So you can imagine a dynamical system, that's fine. So with finitely many degrees of freedom, okay? But then, so we will have to care about various things, global time existence. infinite volume limit. Okay. This would be the global time existence, for example. Okay, that will be our first problem, maybe even on the Tuesday if we are fast. And then okay, so and then we will make, so this will give our basic object in a very simple set. Okay, the point of the lecture is study a given dynamical system in finite dimension. This dynamical system is motivated by this Euclidean quantum field theory story, which we described at the beginning. And then this dynamics we study first with finitely many degrees of freedom, globally in time. This already introduced some technical problem which we want to solve. And then we want to take what is called the infinite volume limit first, for example. So this introduces infinitely many degrees of freedom in a very specific ways, and we want to control. So control of the infinite volume limit. So this is the first part, and then the control of what is called ultraviolet limit. Okay, so small scale limit. Okay, so these are the two problems I announced before, and then one would like to control them. And the infinite volume limit, somehow it's not so difficult, but requires some care. And the control of the ultraviolet limit, so if you want, this is like statistical, correspond to a problem of statistical mechanics, okay? A typical problem in statistical mechanics. Okay, you have a system which has like atomic scale. So you have discrete objects in the system, and then you want to take a large number of these discrete objects, but somehow they locally all interact with infinitely many of them. So there is not much difficulty locally, but it's a problem of the behavior of the system. And then want to control also the other limit is the situation where in every box you start to have more and more objects, okay? Because somehow you don't have you don't want to have a very specific microscopic scale, okay? In this problem in Euclidean quantum field theory there is no this scale, so you have to remove this regularization, and you want to control this ultraviolet limit, and this will introduce, so this will be maybe all the second week, will require all the second week, because yeah, so we will need to develop tools. We need need tools to deal with this situation. And the keywords will be in this lecture. I would not be able to review all possible approaches, so we will choose one which is the one I'm familiar with, and which has been used in a paper to deal with the problem we want to discuss, and which is the paracontrolled calculus. And okay, there are actually another key idea which should come before logically, is the idea of renormalization. Because one has small scale singularity. Okay, the idea is that products, you will have products of distributions, and as you may know, I mean, you cannot multiply two distribution without being very careful of what you're doing, okay? And that's introduced the idea of renormalization and technical tool of paracontrol calculus, which I hope to explain. This require maybe a bit of analysis, but and then the keywords here, if you want on this part, of course, will be yeah, product of distributions, paraproduct, Schauder estimates. Okay, so if you want, this is PD tools. Okay, so PD So the idea is, surprisingly, somehow the kind of tools that works well in this situation are not probabilistic tools. So there is a mix of probability and analysis, but essentially a lot of PD theory tools, okay, which we try again, okay, to introduce. And maybe, yeah, and at this point, we will be able to discuss local existence and uniqueness, for example, okay? And then another step, so, but this is, now we have all the tool, okay? We know somehow in a simple situation how to control the infinite volume. We know in us infinite volume, if you want. So I separated the two problems, okay? You have a two problem and you can separate because you understand how to deal with one without the other, and reverse, the converse. And then you put everything together, which at that point should be easy, okay? And somehow you want to prove, yeah, okay, you want to prove a lot of things about the model. So you essentially, in our context, will be tightness of a certain class of probability measures, of certain family of probability measures. And then, okay, some properties of these probability measures, and these probability measures will be will give rise to an Euclidean quantum field theory, and then by proceeding backward to a quantum mechanical problem. Okay, but we will not maybe. Okay, and these are maybe some of things I would like to, but this is tentative. Okay, at this level. And then if there is time, I want to speak of some other themes. So at this point, if we have time, I want to touch other things which are like so this is how you handle, so how you use the technology we introduced to prove that certain microscopic model looks like, I mean, how they look like in the large scale. Okay, so so we will study a very specific model, but actually what will happen is that a very large class of problems, okay, a large class of problems, maybe not very large, but somehow not all, they have all this same limit. Okay, so they all converge to the kind of this measures we construct in the core of the lecture. So I would like to give some idea about how does it work, and this is called weak universality. Okay, somehow the model we construct looks strange somehow. Why this model and not another one? And the reason is that somehow, yeah, it's a specific model, but it contains somehow the limit. It describes the limiting behavior of a larger class. Okay. And then maybe, okay, there could be, if there is time, I will maybe try to discuss some other situations, okay, which, just to give you an idea, this maybe I could even do before somehow, because yeah, okay, let's see how does it goes. Okay, so somehow stochastic quantization, I think my point of view is that stochastic quantization means a very general statement, and one can implement in various ways this idea. Okay, and this the way we use in the core of the lecture is using fictitious time and what is called a Langevin dynamics. But there are other ways to implement this idea, and they give rise to different kind of equation. Okay, so the dynamics we will study in the lecture will be parabolic, but you could also study an elliptic dynamics, an elliptic equation, so without any dynamic, or hyperbolic equation. Okay, there is no advantage so far, but I think conceptually it's very interesting to know that the approach is not restricted. Okay, and there is also a variational formulation, that is, you formulate the same problem, but from the point of view of optimal control. Okay. So there are various ways of implementing the same idea. We focus on one because I want to give some more detail, but you should keep in mind, and maybe at the end of the course, we will try to enlarge our horizon, optimal control. Okay. But you see, all these ideas might introduce some PD aspects. Okay. So if you want in this course, I want to stress the fact that we use PD arguments. We will use a mix of PD arguments and probabilistic estimates. Each of them separately cannot do the work, so we put them together and we try to get what we want out of them. Okay, so this and the plan. Somehow it's very tentative. I hope we at least arrive to this part where we put everything together and I am able to show you the existence of the model. But in case, okay, so why? Yeah, sorry, I have a problem here. Okay, good, that's better. Okay. Okay, that's the plan. Okay, so we can start. And as I told you, I want to spend some time at the beginning to motivate what we want to do. Okay, because I find it interesting. Yeah. So let me.
Sorry.
Yeah, please.
May I ask you a question?
Sure.
Yeah. So I wanted to ask you: are there any relation with the Liouville quantum gravity in all what you're discussing, and do you plan to discuss it?
So there is yes and no, yes and no. So there is relation, yes, in the sense that you can use maybe you can use stochastic quantization to construct or to study Liouville quantum quad. So I will make the point. So let me let me write. Yeah, so yeah, there will be a link because stochastic quantization is a general tool to study probability measures. Okay, that's I mean, I can put it really right like that. Okay, so it has been applied to Liouville quantum gravity also. There are some work of Garban and others. So what I'm not sure if so the idea and the technology could apply. Now I will focus on one specific model because the same idea could be used for other models, but then all the details are very different and all the problems are different. This is like in PD theory, is like in PD theory, okay, very different equation. You have to use different technology to overcome the problems. Okay, there is no general there is no general tool which overcome all the problems. Okay, there are tools which overcome certain class of problems. So I think the idea applies. Okay, then I will not use it, and I will not mention it maybe in the course of the lecture, probably at the end. Okay.
Okay. Thank you. Thank you.
If you're interested in Liouville quantum gravity, I will not use it. So Liouville quantum gravity is a specific model in 2 dimensions, which has certain class of problems, singularity problems, and which can be renormalized. So we will use as a leitmotiv another theory. So if you want, I can write the aim of the course is, yeah. So my aim is to illustrate an idea, okay? And I want to use a very specific example because I want to give you all the details. So I want to construct a specific measure on a space of distribution, which is called, yeah, okay, so which is called the 543 Euclidean quantum field theory. Okay, so let me, so let me give you, some yeah, so let me give you some idea, some initial idea, for example, okay? And okay, this is more or less what I said, okay? So Euclidean quantum field theory are, okay, I still don't give you an example because I want to motivate the example. So just take it as abstractly as these are probability measures on space of Schwartz distribution. That is, they describe the law of a random variable which takes value in a space of distribution over an Euclidean space, okay, RD. And they are motivated, okay, and our motivation, we want to think of them as model of relativistic quantum mechanics, okay? So as I told you, so my definition, so this is, okay, I will define a bit more precisely what is an Euclidean quantum field theory among all the possible distribution probability measure on this space, okay? It has to satisfy other properties, but what is stochastic quantization, okay? So I want to give a definition which seems very broad, but somehow capture the spirit of the lecture is stochastic quantization, okay? There could be many. So you give me a probability measure, or I want to study a probability measure, mu, and then a stochastic quantization is a pair of a map, f of mu, and a Gaussian random variable w, such that, okay, when you take the Gaussian random variable and then you map through the function f, you get something, a new random variable, which has the law mu, okay? So this is what means to me to have stochastic quantization of a given law mu, okay? And so the idea I want to develop in this lecture is I want to explore the possibility of obtaining as many information as possible about this measure through this stochastic quantization map, okay? Yeah, okay, so this is okay, so now, I mean, you can start to complain if you, but okay, with respect to the previous question, okay, you could imagine you have mu is the Liouville measure, and then you want, makes sense, okay? You can ask, can I do a stochastic quantization of the Liouville measure? That is, can I take a very nice and easy source of randomness, okay? So the Gaussian, that, okay, that W is Gaussian is a choice, okay? Is an arbitrary choice. Okay, you could imagine you just start from another random variable, okay? We know Gaussian variables are very well understood, okay? So make life easier for us. Okay, that's the choice. Okay, you choose because, but why in this definition you choose a Gaussian? Because it's an easy object. Okay, and I don't know other example. I don't know interesting examples where W is not Gaussian. Okay, in stochastic analysis you can do things maybe with Poisson processes, but essentially it has to have some kind of feature like that. Yeah, so, and then, so as I told you, there are various possibilities on the choice of mu, okay? And we will concentrate on two things. First, we fix only one measure. I will not consider many measures, or in particular, I would not consider the Liouville quantum gravity, for example, or other models which we could consider. I will fix on what is called 543. So I will try to explain what is 543, and I choose it because it's not so easy, but is somehow doable with this technique. At least something is doable with the technique I want to show you. So it's a good test for the approach. And okay, and then in the 80s, actually, Parisi and Wu, which introduced somehow this idea that you can construct a stochastic quantization by introducing a fictitious time. And then, so there will be a time in our discussion at some point, not at the beginning. So there will be a time which is not the real time. Okay, time will have be disappearing from our picture. There will be this measure on a space of distribution. Okay, on RD, there is no time in the measure mu anymore. But we introduce a time which is arbitrary, and we will try to describe the measure mu as the invariant measure, some invariant measure associated to a random dynamical system involving this time. Okay. Okay, so and let me define. So I have a goal here. I don't want to describe any measure, but I want to describe what is called Euclidean quantum field theory. So just to fix the idea for us, so what is an Euclidean quantum field theory? For us, it's a probability measure on the space of distribution which satisfy three properties. Okay, so these three properties I didn't define. Okay, so just keep in mind that it has to satisfy certain requirements which we'll introduce later on during the lecture. So reflection positivity, Euclidean invariance, and certain good estimates. Okay, the certain moments should exist under this measure. Okay, Euclidean invariance, somehow I hope it's clear. Okay, so means that somehow the measure, okay, so the measure, it's a measure on the space of distributions. Okay, so somehow you take a test function, then you test the random variable which has this law with the test function, and then somehow the law of the result should not depend where you put this test function. And that's somehow what does it mean? Okay, so somehow the measure should not prefer a region of space with respect to another. Okay, so should give the same probability. So you should see the same thing in every region of space. Okay. When we have a specific model again, okay, it will be clear what it is and what does it mean. But for the moment, just keep on this intuitive picture, okay? And reflection positivity is a strange property which I need more definition to introduce, okay? But it turns out, so I just give this very vague definition because it turns out that it's not easy to construct measures which satisfy all this property and are interesting, okay? You can construct Gaussian measure which satisfy these properties. You can look at some non-Gaussian measures somehow, and somehow non-Gaussian measure, interesting non-Gaussian measure which satisfy this property are not very easy to construct, especially if D is 3. And actually the only one we know, as far as I know, it's 543, okay? So for D equal 3, the only known example of a Euclidean bosonic, okay, let me say it's a bosonic. Yeah, but I think that's why. In the above sense, this sense is 543. Okay, so 543 is a class. So I didn't define, but just to say, okay, so we are interested in it because if you take D equal 3 in this definition, then essentially I know only this example, if I'm not wrong. Or at least I understand only this example, okay? I think you can construct okay, let not be, I'm a bit worried because I don't master all the literature myself. So please comment if you have remarks on that. So an interesting an example. Okay, let me, but it's the only one I know and I understand. Okay, maybe there are other, maybe Balaban constructed young Mills, but okay, young Mills does not really enter into this definition. Okay, it's 543. Okay. Yeah, okay, so we want to prove, in particular, the goal of the lecture is to prove the theorem, okay? So let me say in this way. Okay, so now, sorry, a moment, I have a technical problem. I forgot to define something. Okay, better, good. Okay, so that's my goal. Okay, if at the end of the lecture we understand, at least on the broad line, the proof of this theorem, then I'm happy. Okay, so the goal is to construct, okay, a two-parameter family. I will prove existence. Okay, I would not prove actually that there is even a unique two-parameter family. I'm not able to do it right now, actually. With the tool I will explain. And we call it 543 model. Okay, and that's the main goal. Okay, so I explain the goal, and there are other measures you can construct. Okay, you can construct 542 or in two dimension. Okay, so when d equal 2, there are many more examples, but we pick up because involves some further interesting consideration. Okay, it's not more difficult, but somehow it's easy. It's not easy, very easy, but it's not very difficult either. In two dimension, you have very easy examples somehow in my language, or very difficult examples. Okay? So here in three dimension, we know only this one, and this is in the middle, and we can solve. Okay, so let me. Yeah, in the notes I will put some bibliography. Okay, I don't want to spend much time to do it right now, but essentially it was so somehow the yeah. Okay, so don't I will put the bibliography, the things in the bibliography, I think.
Sorry, can I ask another question?
Sure.
So in 543, 3 is the dimension and 4 is standing for what?
It's a number for now. It's the fact that it will be constructed as a polynomial of order 4 with an interaction given by a polynomial of order 4. Okay.
Okay, and so you plan to construct it as a stochastic quantization, right?
Yes, so that's the goal. So somehow, yeah, because okay, the problem is also what is this measure? Okay, so somehow I cannot describe to you what is the goal. No, I cannot say okay, I want to define an object. It's not easy, at least, to say to characterize the limiting object, and I don't know of any useful characterization. So somehow how it's defined is that you take a proximate object and you try to take the limit, and the limit you call 543. Okay, it's a name for now. I don't care. Just to name this object. Okay, so in the literature is defined as this limit. So why it's interesting for us? So that's what the point I wanted to make is that somehow I want to make a go. So I want to enter into this subject by this point of view that somehow in order to have interesting model of quantum mechanics, you have to construct a measure which satisfy these three properties. Okay. Now, I think the interesting point to me is when I realized that it's not easy to, in three dimensions, to satisfy these three properties. And the only example, so Okay, so it's not the unique measure which satisfies these three properties, but you don't know other easy examples. Okay, and actually, so it's already quite difficult to construct this one. Okay, so this is an example of a measure which satisfies these three properties, and these three properties are important because then out of this measure you can construct a quantum mechanical model. Okay, so that's the interest for us. Okay, so you can forget why that's my motivation. Okay, I'm not interested. I will not try to motivate. I will just say, okay, you can put, if you put other numbers here, I cannot do anything. Okay, if you consider cubic interaction of fifth order or sixth order interaction, I cannot prove anything. Actually, it's getting more difficult as this number get larger. For the cube, I cannot do it. Actually, you should maybe not, does not make any sense as soon as you see what does it mean. And for the square, it's not interesting because it's Gaussian. Okay, so somehow is the only example I'm able to understand and show you of an object which satisfies definition 2. That should be my motivation for us here. Okay. So just, okay, so if you want the lectures of the problem, show me an example of an object which satisfies definition 2 in dimension 3. And that's the only way I know how to do it easily. Okay, in a way I can explain easily. It's not very easy, but I think I can explain to you. Okay, so let me again. Okay, so that's the, or maybe you should ask a question at this point if you feel uneasy with something, because I try to make definition and theorem just to fix the key point. Okay, so now I define what is a stochastic quantization, in the sense that if I show something to you, you should be able to realize if it fit or not this picture. I somehow define what is Euclidean quantum field theory as soon as I define for you what will be this property, because essentially these are the properties. Okay, I would not ask anything more than that. And then the constraint, somehow the idea is that something which satisfies this definition is not very easy to construct. Stochastic quantization will help us because somehow we will be able to construct a map which map a Gaussian random variable, infinite dimensional but Gaussian, into a random variable which satisfies all these properties. Okay, that's the difficulty. Okay, and I know only one way to do it, which does not give a Gaussian or something which looks very much Gaussian, and it's to construct 543. Okay, so now so this fix a point in our discussion. So let me give a broad. So yeah, I gave me an ambitious goal for the beginning. Okay, so I want to really motivate this from our point of view, and I need to. Yeah, maybe it's too ambitious, but let's try it. Okay. I will say it's the first time I gave the lecture in this way. So let's see how does it go. So please, in order to be successful, you have to ask questions. Okay. If I think it's not pertinent, then so what is quantum? I will just say it's not interesting for the rest of the lecture. So, but. What is, so I have more detailed notes, so I will send you the notes. Okay, so in the notes I will put references. Okay, but I want to use the point of view which I learned from a book of Strocki on mathematical elements. Let me see. So if you want to, yeah, let me put some reference for you. Sorry, my computer, it's slow. Okay, so what is quantum mechanics? Okay, so quantum mechanic theory. So let me see the point of view. I'm not claiming that's okay. That's, I think, the point of view which I find interesting and explaining. Okay, so it's a theory of measurement. okay, here, at least in this lecture. Okay, here. So what is the basic structure of a measurement? Okay, you have we have observables. Okay, so these are things you want to measure. Okay, and this could be I really imagine very concretely. Okay, an experimental setup, and then you have a gauge, an indicator, something you can get a number out of it. Okay, and then a set of states of a physical system. Okay, so you choose is a game. No, you have two players. You choose something, and then on the other side you have the nature, which give you a state of the system. Okay, and then you put these two things together and get a number. Okay, and so therefore you assume that for every observable in any state you can form a number. That's the structure. Okay, the initial structure. Then somehow what is this number? Okay, in practice this number, it's very clear what you do. Okay, you repeat an experiment in time. Okay, so it is postulated that the empirical mean of repeated experiment results. Okay, then you imagine you have a family of results of an experiment of measuring some observable, and then convergent, the limit is what you call this number you receive. So this number has to be interpreted as what you observe in a series of repeated experiments where you put your system always in the same state and you always observe the same observer. Okay. And then yeah, so you have some structure. So let me, so you have structure on these observables. So for every observables, I can measure both of them, and I can measure both of them, A and B, and then I call it the measurement of A plus B. Okay, so I say, okay, I impose this relation. So what does it mean, measure A plus B? It means measure A and measure B. Okay, and then of course you can multiply with a constant. Okay. And and then I can also measure any function of an observable. I mean, this would be very long discussion, so I want just to give a feeling of what could be a formalization. Okay, so you can imagine, okay, if every time I measure an observable, instead of registering xi, I register f of xi, a function, then I say I'm measuring the observable f of a. Okay, and you can take any bounded function. Okay, that's I think it's a reasonable requirement. Okay, so next step is that, okay, you can measure the constant function, the constant observables. And of course, when you measure the observable, there's always give the value 1, then you register 1 on any state. Okay, and if you measure a positive observable, then you get a positive result. Okay, so, and you can say, okay, an observable is positive is just the square of another observable. Okay, it means that every output is positive. Then comes interesting fact. Okay, then I can measure, I told you how to measure a square, b square, and how to measure a plus b. So I can measure also a plus b squared. Okay. And then you can define a product by polarizing the square. Okay, you can say a per a star b. It's just what you would get. Okay, you define it like this. Okay, and this gives you an algebra. Yeah, okay, so then you wonder, okay, what is this algebraic structure, okay, where somehow, yeah, you see, it's strange, okay, you don't postulate you can multiply things, you say, I can only do the kind of thing I told you about, okay, so you sum things and then you can take functions of things, but you cannot directly multiply two different things, okay? And then, okay, this is essentially is what it's called a Jordan algebra, and there is an interesting Wikipedia article on it, so you can give a look. And then it turns out that, for example, in finite dimension, you don't have many choice, okay? So this is the minimal requirement you would like to make for a measurement, theory of measurement, let's say. And then you don't have many choices, okay? And I actually learned recently that yeah, you have it's very strange. Okay, you have so finite dimensional Jordan algebra can be classified. Okay, I didn't explain to you what are all the axioms, but think they follow from these considerations. Okay, then you give a well-defined set of axioms, and then you find that actually you can have only finitely many kind of things. Okay, so either these are matrices, it's an algebra of metrics, which could be real with complex real quaternion coefficients, or okay, it's a finite dimensional Clifford algebra. Okay, or it's a or you have octonionic matrix with octonionic entry, which I would not would have difficulty to explain what it is exactly. But somehow the interesting fact is that if you use this field, then you only allow only algebra of matrices 3 by 3. Okay, of course you can have numbers. Okay, you can have one-dimensional matrix algebra. So these are just real number, complex number. They all satisfy these requirements. But for octonionic, you have only this case. So this is very strange. Okay, so they can, yeah, whatever. Just curious fact. And then, okay, then now this is the jump which you have to make at this point if you want to make many progress somehow in this business, and you have to choose. And nature seems to have chosen for us that the observable algebra, it's made, so it seems that it's compatible with what you observe. We observe that we take this complex, among all these choices, we take the complex numbers to make these matrices, okay? Okay, so that's an assumption, okay? So somehow before was everything was quite reasonable, and then here you have to make an assumption. You don't have reason to choose one of the other, apart from the fact that somehow it seems that if you want then to stick to make your theory agree with the physical experiment, you have to choose complex numbers, okay? The algebra made by complex numbers. Yeah, okay, maybe, by the way, all this consideration, yeah, I have a hand raised. Yeah, you can just interrupt me, maybe it's easier to me. So if you want to ask a question. There was somebody raising hand. I'm not sure if it was.
Yes, it's me. I wanted to ask if, so what is, I missed, due to technical problems, I missed about a minute of your lecture recently.
No
and
problem.
So what is in the end the observable? Is it a matrix or is it something else?
So no, but okay, that's interesting question. Okay, so let me put here a reference. Just for example, if you want to add more detail on this point of view, you can look at the book of Strachey. So let me just put a moment to the reference, then I answer your question. Okay, just I've just found. So there is this book of Strachey, or in Bonn, I gave because I wanted to learn this stuff. I gave a course last with Francesco De Vecchi. We gave a course. And then we just wrote lectures. Sorry. Okay. Okay. This is summer semester 2020, and you find them here. Okay. Then I answer your question. So yeah, that's what I found interesting when I discovered this fact is that you don't say what is an, so that's it's a set. Okay, from the point of view of this formalization, it's a set. Okay, so you have a set. In this set, you have observables. Okay, they have to satisfy these requirements. Okay, you see, you don't say exact, you don't need anything. Okay, so the observable is just something which does not have a priori structure. Okay, you introduce a structure in this way. So somehow, if you want, okay, a posteriori, let me say, in this formalization, what you say, you try to motivate reasonable axioms. Okay, so at this level, I motivated that the axiom should be a Jordan algebra. Then you can say, okay, an observable is a Jordan algebra, provided you gave you gave the right axiom. Okay, if you want. Okay, then you look, okay, what are the Jordan algebra I'm available? And then you look that for, let's restrict to finite dimension. For finite dimension, you have only these choices. Okay, if you want to fulfill the axiom of a Jordan algebra, which are motivated by my interpretation of this mathematical object in the context of a measurement theory, then you have only these choices. It's clear. So it's not anything a priori, but somehow you want an object, a mathematical object which satisfies certain prerequisite, and you have only so many choices to choose. Okay, so, and it seems so. This is where you could choose any of these. Okay, but somehow to make an interesting theory, which could fit with nature, with somehow have some relation with nature, seems that you have to use the complex self-adjoint matrices. Okay, so for us, the observable algebra is the algebra of complex self-adjoint matrices. Is that an answer satisfying you?
Yes. Okay.
Okay. Yeah, that's fine. But okay, I will say that this is a point where you, so at the, I think I find very, so this is in the book of Strock is very somehow very well motivated. I think the book, yeah. In our lecture notes, what we try to do is that really stick to this approach as far as possible. Okay, you try to introduce less structure as possible and see how you can, where you can go. Now, so here it's motivated. Then you at this point you have to make a jump. I don't see. Okay, I don't see any particular region zones for that. Okay, there is no particular. There seems to be no particular mathematical reason for this. Okay, so you don't see any difference at this level between various choices. Okay, so I don't know how to justify. So but if you want to make a progress, you have to assume. So this is a postulate you have to make. Okay, but again, okay, it's not that. So somehow you are looking, the observable are the self-adjoint matrices. Okay, so you are taking not all the matrices, or not all the complex, only the observable are the self-adjoint elements. But the fact that you have complex number, give you additional structure, and then okay, then you can abstract a bit, okay, from matrices and consider, okay, let's see, I don't want to have finite dimension. So how I describe abstractly this algebra of matrices without using the fact that they are matrices, and what are the important features. And the features is that one can a bit abstract from this. So this is okay. This is an important point. Okay, but in the feature you abstract about this, and you take just a sister algebra A instead of the algebra of all the matrices. So you say the observable. So now I specify a better the setting. Okay, so this was motivational. So observable for us will be the subalgebra of self-adjoint elements real. of a sister algebra A. Okay, and what is a sister algebra? Okay, think about matrices. Okay, that's not very complicated. So you have an algebra of matrices, you have a norm, what you have for complex matrices. Okay, you have an involution, which is the Hermitian conjugate, and you have a norm, which is the operator norm, let's say, of the matrix, and then you verify that you have this condition, okay, which seems meaningless. Okay, this you can verify. Okay, if you take an algebra of matrices, okay, an algebra of complex valued of complex matrices. Yeah, I think I'm right. Okay. Yeah. Yeah, let me just copy from my. Yeah. So if you take involution, the Hermitian conjugate, and the norm as the operator norm in the associated base space, then you see that you verify these conditions. Okay. Now, what I found also very interesting is that this condition, it seems innocuous, but it's really quite powerful. Okay, so what is a sister algebra? It's just a Banach algebra with a complex Banach algebra with a conjugation which satisfy this condition. Not all the complex Banach algebra they satisfy this condition, but essentially think about the matrices. That's okay, and you can take also, okay, now if you want an example of sister algebra, another sister algebra is, for example, bounded function on some, okay, the algebra, the complex continuous bounded function. Actually, you don't. Yeah. On some topological space. Okay. Yeah, I don't want to be, okay, think about yeah, okay, like C01, okay, just to be clear, with complex values. Okay, so that's sister algebra. So with the supremum norm, okay, with the supremum norm. Okay, that's you verify that satisfy this condition. Okay. Okay, so that's the formalization. Okay, and so this would be it's an algebra. Okay, so we have to understand what kind of algebra so okay, that's too general. Okay, we have to be more specific, and then so the first observation we have to take into account is that actually this example, it's somehow quite universal in the sense that there is a theorem that if you have, now I didn't say that the algebra is non-commutative. Okay, so indeed, okay, you could take a matrix, but you can take one-dimensional matrices, then you have a one-dimensional algebra. But okay, as soon as you allow any sister algebra, then you have the situation where the sister algebra is commutative. Okay, so for example, this example, the continuous function in 0, 1, you multiply with supranorm and pointwise multiplication. Okay, you have to specify you take the adjoint, so the adjoint and yeah, is the, how do you say, the complex conjugate as adjoint. Okay, so it's such an example. So, and then, yeah, and then you have a theorem which tells you that actually any commutative sister algebra is essentially an algebra of functions. on a compact space. Okay, you don't know what is the space a priori, but it could be complicated, but that's the case. Okay. So commutative sister algebra are algebras of functions. Okay, and do we like them or not? And the point is that if the algebra it's continuous function, okay, why the commutativity? Why I bother about commutativity? The point is that if you are, okay, any commutative sister algebra is an algebra of continuous functions, and this has implication for the theory of measurements, because somehow the following fact is true. You can think about, so now you have states. Okay, states are states are in the dual, so they are you take them to be continuous because you introduce a topology in the formalization. So you have a state, a continuous linear functional, positive functional, which is given by valuation in a point. Okay, so I mean that's clear. Okay, you take any an element in the algebra is a function, and then a state delta of x is just evaluating the function in the point. Okay, because by Gelfand theorem you have this compact space around that represent your algebra faithfully. And then you prove that actually any other state it's a converse combination of such states. Okay, don't want to enter into the detail, just want to give you this geometric picture. Okay, and what you have here. Okay, so you have an algebra of functions, you have measures on that. Okay, that's what he's saying. He said that any state is a measure on the functions. Okay, and you by taking the average of the function you get the duality between state and observable. Okay, so if your sister algebra is commutative, you have essentially the theory of measurement that we wanted at the beginning. It's a probability theory. Okay? You just have probability theory. In particular, you can find a state, delta of x, okay, in which every observable has a precise value. Okay, so in this case, okay, so what is the value? What is the product AB? Then it's just XA times XB. Okay. And that's not what you observe. So that's against what you observe in nature. Okay, in nature you observe that. Okay, it seems to observe that that you cannot measure. That there are observable which you cannot measure with infinite precision at the same time. Okay, or if in one state one observable is very precise, then another observable has a large variance. Okay, so this somehow is the next step in the formalization. And yeah, you need to admit no commutative. Let me maybe try to put a symbol on the things I find interesting. So let me put this. So somehow we had 3 steps. Okay, now our formalization is okay. We start deciding this, that we have stated observable. And then you take sister algebras because you want to generalize this idea that in the nature things seems to go through in this direction. That is, you have complex numbers somehow, and you have an involution. Essentially, you have this involution around. And then the commutative sister algebra can be measured. You can measure things very precisely in commutative sister algebra. And then you have to allow non-commutative sister algebra, hoping that you can escape this problem. Okay, and actually it happens that you can escape the problem. Okay, and yeah, and then you discover. Okay, then you can think a bit and you can make example. You can look at the lecture notes if you want to see the example, but essentially you can make, with non-commutative, okay, with non-commutative sister algebra, one can make very finite dimensional. So you can take an algebra of matrices, for example, and make you an example in which you have two observable with two observable. Okay, yeah, let me just state with two observable, one very precisely measurable. Let's say that if you measure one in such with two so you can construct two observables, and if such that if you measure very precisely, then sorry, I think it's misleading said like this. So let me so such that if in the state omega one is very precise, it is a small variance, then the other maximally spread. Okay, I don't want to be precise at this level. You can look in the lecture notes if you want to see this example. Okay, so every random variable, when you look only at one observable, then somehow itself it generates a commutative sister algebra. Okay, because all the functions of this observable commute among each other. Okay, so as soon as you look at only one observable, you have a probability theory. Okay, the things interesting happen where you are in a context where you have two observable which do not commute. In that case, you can show that you cannot construct this delta function does not exist. Okay, if in a state one observable is very precise, then another observable has to be, the other observable has to be broad. Okay, and you can construct very easy finite dimensional example. You don't need a lot of technology, okay, to understand this. And actually it's very useful to think to these finite dimensional examples. Okay, so that seems interesting for us, okay? The modelization, non-commutative sister algebra allow this fact that you cannot find state where all the observable are measured at the same time with infinite precision. That's good. And then there is this beautiful fact, that's why people are got interested also in sister algebra, that you have a very nice representation theory for sister algebra. So sister algebra, so there is this theorem, so the Gelfand-Naimark theorem, which states that sister algebra can be faithfully represented in Hilbert space as a subalgebra of the algebra of bounded operators. Okay, so any sister algebra. The Hilbert space, maybe it's okay. It's not separable, I think. Not sure. I'm not sure if. Yeah, I should check maybe. But okay, for us it's enough just to maybe understand this fact. Okay, so let me. That's the but that theorem it's very nice for application in algebra. But so somehow it's very concrete. Okay, so essentially this make appear for the first time in Hilbert space. Okay, somehow I prefer this way of formalizing things where the Hilbert space is not the first object you introduce because it's never clear what does it mean. So in this way of formalizing things, Hilbert space is a tool. You don't have it. Okay, you should not have it for interpreting what you're doing. It's just a mathematical tool which make life easier. In particular, allows you to represent this abstract sister algebra in a very concrete setting. Okay, you have an Hilbert space, and you have a bounded a subalgebra of all the bounded operators. Okay, but inside this theorem, there is I think this theorem was proven by Gelfand and Naimark, and in the construction, in the proof, there were a nice construction which which then Segal somehow put more in use. And this is called the genus construction, which is very interesting because somehow for application in quantum field theory, that's more interesting than the general theorem. Okay, so I put it as a theorem. And so please ask, I know that somehow I'm not very precise in defining and stating things, but I wanted just to have a broad overview of these facts, okay? And but if you feel puzzled, you should ask precise questions again, okay? So this construction tells the following, okay? So we have a sister algebra, and you give me a state on the sister algebra. So this is positive continuous linear functional on the sister algebra. Yeah, let me yeah, okay, let me mention the involution allows you to define what is positive, okay? So a positive element is an element, so a positive element, you say, okay, as a positive element. So in a sister algebra, you have an abstract notion of positivity. Is an element of the form I equal B star B for some B, okay? Now that's also quite nice in a sister algebra from some self-adjoint B, okay? Let me, okay, no, for self-adjoint I don't, sorry. Okay, for some B in the sister algebra. Okay, so you have an abstract notion of positivity and then a positive state is a linear functional on A, which is positive on positive elements, okay? Yeah, sorry, maybe I should have said before. Yeah, and normalized, okay? It is, okay. Sorry, yeah, I always get confused. So, a state in general, so I'm more precise what is a state apart from the initial discussion, vague discussion, just you have a linear functional, which is positive on positive element and normalized, that is omega 1 is 1, okay? So what does mean positive on positive elements? This means that omega on the, okay, we've seen the all positive elements of this form, so this has to be positive. And then it's continuous, okay? Automatically. That's also very nice. Yeah, so if you give a state, so you see, you have the abstract algebra, and every time you give a state, then this producer, by this construction, some objects, so three objects produce an Hilbert space. So I put depend on omega because they depend on the state where you, and of course on the sister algebra, okay? But they produce an Hilbert space, a representation of the sister algebra. So that is, okay, you have a copy of, not a copy, but okay, okay, representation, okay, homomorphism of the sister algebra into a sister algebra of the bounded operator on the Hilbert space, and then a specific vector of the Hilbert space such that the value you are interested in, that is the value of any observable, any element in the sister algebra actually, but in particular the observable on the state omega, is given by, okay, you see where the element, the representative of the element A in the Hilbert space, and then you take a scalar product with the state phi, okay? So that's somehow, you see, this abstract object, which maybe it's not very clear how to work with what is called, I mean, how you put coordinates on a sister algebra, okay? How you compute numbers out of it, okay? How you control that things are fine, okay? So in a manifold, you have Atlas, and you can imagine that in this GNS construction give you what the same thing, okay? That is, give you charts somehow. So for every state, you have this representation, and every time you need to compute expectation with respect to the state, actually, it's to it's equivalent to compute these averages, okay? And if you know a bit of quantum mechanics, that should be maybe familiar to you at this point. If you don't know, you don't care very much. We will not use it much, but that's important because that's the way, somehow that's another reason why sister algebra are used, is because they have this nice theory of representation. And then the representation, so this representation cannot be simplified, so cannot be written as a product of other representation, simpler, if the state is pure. Okay, so what does it mean that a state is pure? This is like more or less in measure theory, that is the set of all state is a convex cone, and state is pure is extremal, that is, you cannot write as a convex linear combination of other states, okay, if it's not inside the cone, but on the boundary. Okay, so you have this very nice relation between the geometric property of the cone of states and the associated representation, the representation of the sister algebra, okay? Okay, we don't use it, but I find very nice to state it.
May I ask a question?
Sure.
What about unbounded operators in this setup?
Yeah, that's a good question. So I myself don't understand very well unbounded operator, and I like this setup because you never see them. Actually, I will try in the lecture, so that's what we tried to do in the lecture in Bonn, which I put to you, never to use unbounded operators, okay? So that's, yeah, I mean, I'm not sure it's the most efficient way of doing the things, but I find intellectually interesting to see how far you can go without using unbounded operators, because you see that's the point of this formalization. It's not clear what they mean. Oh, of course, you will see later on that they have a clear meaning, but somehow they are not operators in this formalism, okay? Does this answer your question? So they will not, they not appear, at least not in the way you think of. I think later on you will need, when we will need, I will try to discuss this, but so far they are not there. So this is the easy answer, because everything is bounded, okay? So the sister algebra, so you see this, a sister algebra is a norm, okay? You can multiply everything with everything else. You can sum everything with everything else. Essentially, an example of sister algebra is the full algebra of bounded operators in an Hilbert space, okay? Finite or infinite dimension. And Gelfand-Naimark theorem says that essentially is the, okay, you can do everything inside that model, okay? There are not more difficult sister algebra, okay? Every other sister algebra can be embedded faithfully without losing any information inside that model, okay? So you can, that's a universal representation space. But then, okay, I think it's more useful for what we do and for quantum field theory to understand that actually, so the Gelfand-Naimark theorem, once you understand this construction, it's very easy, okay? You just tensor this construction for every possible state, and then you have a faithful representation. So the key point is really how you construct a representation for every given state, and I think the proof is very beautiful. It's not very difficult either, but give you this insight on the structure of these things and make appear, so the Hilbert space appear at this point, okay, where you choose a state, this fixes an Hilbert space. If you choose another state, there is no reason the Hilbert space is the same or the two are isomorphic, or even unitarily equivalent. Okay? And unbounded operator never appear because all this, the representation has to be done with bounded operator, because the norm here on the Hilbert space is the operator norm. Okay.
Okay, thanks.
Yeah, but you will see later on, we will have, I work hard never to use unbounded operator in this lecture. No? So maybe I work too hard, but I find interesting to see how far you can go. Okay. Also because it's I don't trust myself when I use unbounded operator. I make a lot of mistakes. Yeah. Okay. So we are at this point. Yeah. Yeah. Sorry. I just want to say what's the next. Yeah, let me, so this is quantum mechanics for us, okay? So essentially, to give a quantum mechanical model is essentially to have understood what is the sister algebra and what happens, and what is the, so what happens when you compute things in a given state, okay? So I should say, you see, you're interested in this is the quantity you want to measure, and that's a concrete way to compute, okay? Again, I think the intuition which works for me is that you put a chart, okay? The Hilbert space is somehow a chart in the sister algebra. Maybe it's a local chart, maybe a given Hilbert space does not allow you to describe all the sister algebra in a faithful way, okay? There is an Hilbert space which do this, but maybe it's too complicated to work with, okay? So here, so the goal actually, so in quantum theory, you want to compute numbers, and actually you want even to do more. You want to, we have to discuss what happens with time, okay? So how time enters this picture, because somehow the scope of physics or general science, that you know something and then you predict something in the future, okay? So somehow time has to enter into this picture. Yeah, I don't know if maybe I want to go in the notes. I put some yeah, let me, so what happens now? So what about dynamics? Okay. And so you see, usually we are used to discuss dynamics in terms of motion of points, okay? So you see, in this language, you never, so you have to give up the idea of points. So points somehow exist. In this formalization, points exist only in the commutative, in a commutative situation, okay? So when you have a commutative situation, then somehow this theorem applies, and you can think to your observable as functions on a given space, okay? And then the point of this space are like the states, okay? Because you see that there are pure states which correspond to points, okay? So if you want to understand what's going on, then using classical mechanics, you have a point which describes the state of your system, and this point moves around, okay? Like in classical mechanics, okay? Here, we don't have points in general, okay? So we cannot discuss the dynamic in terms of point. Then you have to think a moment, and then the right point of view. In the notes, I put some more detail, but the right point of view is to introduce an automorphism group. So you have a group of automorphism of the sister algebra, okay? Okay, so what does it mean? okay, I mean, it's that it preserved the product. So let me write the elements with, okay, preserve the product, preserve the structure of the sister algebra. Okay, so it maps sister algebra into itself by preserving structure. Okay, so it maps an observable into another observable in particular by preserving the structure and preserving the conjugate. Okay, that's all you need in life essentially here. Okay, and yeah, in sister algebra, sister algebra are rigid somehow. I didn't discuss it, but it's very interesting that the norm, it's essentially unique. So either you can have either you have a norm or you don't have it. There are not 200 norms on a sister algebra. There is only one norm. Okay, so as soon as you have an automorphism, somehow it has to send the norm into the norm. Okay, because somehow algebraic, they are very rigid objects which are characterized algebraically. Okay, so you have a group. Or what does it mean that it's a group? That is, okay, if you take the sum, you can just do it by applying one and then the other. Okay, and that's the right point of view, and you understand if you think about how the dynamic of points affects the functions on the space, and then they are affected exactly via an automorphic group. Okay, the dynamics transport the function in the phase space if you look at a classical system or dynamic. So this is a common point of view in dynamics. No? So the goal, yeah. So I have now specified somehow. We have enough data to specify what is our goal. Okay, so the goal of quantum mechanics is to establish particular, so abstractly, okay, at least in a way conceptually, is conceptually and mathematically interesting to think about it, is that you have to establish what are the observable, what is the state of the system you're interested in, and what is the dynamics of the problem. Okay, so you have this triplet to determine, and once you have determined this triplet, this is your quantum mechanical model, which contains a part which is kinematic, that is, you describe what are the objects that move around, and a part which is the way they move around in time, the way the things evolve in time. Then you can start to, so what is this time dynamic? Okay, the idea is that somehow you should be able to look at your system at different point of times. And then, okay, so somehow the system has to be the same system. No, it's like why I'm here today and tomorrow, okay, because I can recognize my shape. Okay, so now I have the same shape today and tomorrow. So that's why you require the dynamic.
I have a question.
Sure.
I was going to ask before you started with this paragraph, so what is the analog of point? But never mind. Now I see A1 up to AN, and they do not reappear in the display. You have in the paragraph, you have given the observables.
Yeah, sorry, because I made a mistake, of course. So yeah, so you could imagine. So yeah, so there are no points. So these are the observables. So actually, let me use. I think I started to use. So these are objects in the sister algebra. Okay, which these are the things you want to measure. Okay. Now this was the meaning at the beginning. So let me give, okay, could be the spin of a particle, okay? Like, so an observable is just something which give you plus or minus one, okay? Spin of a particle. Is okay? In a commutative setting, it's quite clear, okay? The observable are the random variables, okay? If you want to think an easy setting, if you are in the commutative setting, observable are random variables. When you introduce a dynamics, you have stochastic processes. Okay, but here the point, and then you could consider the point that is, as soon as you have a probabilistic setting, you have somehow a space where the probability measure exists. Okay, because everything commutes in that setting. Now, as soon as you allow non-commutativity, you lose points. Okay, there are no global points. Okay, because different observable cannot have precise value in the same state. Okay, so you have somehow points which are good for one observable, but they don't describe the other observable. So that's the difficulty. So you have to use a language which is more algebraic. So instead of thinking of motion of points, you think of motion of observable, and you require that the dynamics is an automorphism group, because somehow you require, okay, what I can measure today on the system, I should be able to measure tomorrow, okay, because it's the same system. Okay, so I can measure the spin today and I can measure it tomorrow. So A is the spin of the particle, and alpha t of I is the spin of the particle tomorrow. Okay, and alpha, yeah, and alpha 0 of I is A. Okay, it's the identity. Okay, so this is what you want to measure. Okay, you want to select a certain number. It could be even the same. Okay, it could be just one A, but you want maybe to measure at different times. Okay.
Sorry, I have a question.
Sure.
Are we in the non-relativistic setting, or we are in the relativistic setting?
At this point, there is no choice. So this will be the framework also which extend to the relativistic setting. Because you see that there is no way out from the fact that you are in a laboratory and the laboratory is fixed somewhere, and you have a frame of reference, and this is the time in that frame of reference. I don't see the problem in that. It will describe also the relativistic setting, of course. No, you see my point. My point is that you go at Geneva, at CERN, and then what they do is that they measure particle today and they measure the same particle tomorrow, etc. I mean, they have a detector to, you see, these alpha are the detectors, no? And then the experimental apparatus is always the same, does not change. So this is the algebra of observable, is what is measured by the apparatus. And then the only thing you have is that, okay, the apparatus exists today and tomorrow. And what they do is that they measure something at some point of time, and then the next point of time, and then the other point of time. So that's, and you describe relativistic problem, okay? Is how this number relate to one of each other, which encode the relativistic invariance of the theory. But the experiment broke it. You have to be in a fixed frame of reference, okay? I think there is no problem. But yeah,
May I ask something else? So
yeah.
the point is, now you kind of go state by state. State is this omega, and that's what you can measure, one state. And then maybe you'll have another experiment for a different state. Is that correct? You will never put more than two states together, or maybe later.
No, I would never put. So a state describe, so I will not, I think I will not need to discuss this in this lecture, okay? You could imagine, a state describe the state of my system, no? Okay, so I have a physical system, this is the state. This is what nature, it's a game somehow, no? Duality is always a game between two players, okay? That's what is interesting in duality. The experimenter choose this part, okay? I choose what to measure and when. The nature choose the state, and then all together, then I do my measurement. This is the measuring operation.
Okay, thank you.
So the state is only one at every time. Of course, you could imagine that you have a very, okay, I don't want to enter into this discussion because I didn't prepare it, so I don't want to be misleading, but you can have two systems. You can have two systems and they have their own states, okay? Because they describe by two different sister algebras. And then you can start to put them together into a larger system, and then you can take the product of the two states. I think this is maybe what you want. And then you can take linear combination of products of the two states in this way. Okay.
I mean, it is not that I want it, but I would like to understand. I mean, it is more complicated than the probability theory where you have points. Now, over there, point is like a state. So here,
No, you.
yeah, yeah.
Yeah. Let's say, but probability theory is inside. Okay, so what I'm saying, so if you feel difficult, is just every time you feel in difficulty, you can always think to probability theory, unless I say this holds only if non-commutative. Okay, so commutative, the commutative setting is a probability theory, as I told you. So in the commutative setting, the state will be a probability measure, and then you just, this is just taking the average. I think I wrote it at some point. I wrote in the notes, but I forgot to. So in the non-commutative, so what is the difficulty for you? Maybe let's, there are no points. That's the only problem. So you have to use a language which does not make reference to points, because points correspond to state. Okay. It means that I can prescribe exactly everything about my system, observing certain number of things. So so there are pure states in the, so if you, okay, let me say differently. In the commutative setting, as I told you here, somehow the notion of a purity of a state, it's important, because somehow you can construct all the states as convex combination of pure state. Okay, so essentially, if you want to understand the problem, it's enough that you understand the pure states. Okay, and in probability theory, pure state are the delta functions. So you have to understand what happens when you measure things on delta functions, because then you can just take linear combination. Okay. The problem is that in the non-commutative setting, you don't have the delta functions. So you see, the notion of point does not exist anymore. You have to think to the points as the delta function of the probability theory. Okay, and in the non-commutative setting, there are no such objects.
And do we understand what are the pure states?
In general, you mean for a general quantum? Yeah, you can when you, as soon as you have as soon as you have yeah, of course we understand. So as soon as you have, you want me to give me me to give you an example in a yeah, so in an irreducible, so let me think if I remember correctly. Yeah, I think every pure state, it can be written in this way. So you understand very well. So it corresponds to a vector in a Hilbert space, and correspond to this particular way of taking the average. I'm not sure if this is the answer you wanted, but
yeah, okay.
So in very simple, let's say if you have a very specific, I don't want to give example because I don't want to make a course in somehow computation in quantum mechanics, but you can go very specific. You can start by the spin 1/2 particle, and then you see that the pure states are what you expect to be the pure state. That is either spin 1 or, I mean, you can label in different ways. Okay. I mean, it's a state which you cannot write as a linear combination of other two states. And you are the vectors in the Hilbert space, let's say. Okay, is it you see the state is this object is not one vector. Okay, is the operation of taking the bracket with a vector. Okay, so in particular. Yeah, okay, maybe I don't, maybe, okay, I have a question in the chat. Yeah, I think it's time to maybe close for this morning. So there is a question in this chat. In some quantum physics problem, the system has some kind of symmetry, from Lorentz symmetry, rotation symmetry. Yeah, so yeah, that's a good question. Somehow symmetries are represented. So let me write it here. Symmetries are represented. It will play a role later on, represented by automorphism of A. Okay. So the fact that your problem has a symmetry, it means that somehow you can make an operation on the algebra and you get essentially the same algebra of observable. But no, like time is a symmetry. Okay, this is what I'm saying. Okay, in particular, for example, time translation are symmetries. Okay, this is a natural assumption. You never think about it, but you say, I mean, I'm time translation invariant. Okay, I'm Massimiliano today and I'm Massimiliano tomorrow. Maybe if they change all my pieces in 20, I mean, at some point I will not be Massimiliano anymore, but for short time, there is an automorphism group which translate me in me tomorrow. Okay, I can recognize my hand tomorrow and my other hand tomorrow, or in the past. Okay, and also in the space you can make the same. Okay, we will do it. Okay, you can measure the spin of a particle here, or you can measure the spin of a particle there. Okay, so the fact that somehow. Yeah, okay, that's not okay. One has to be more precise how to say this. Okay, let me stop here because it's already 2 hours that I talk.
Excuse me, I have a question.
Yeah, I will continue in the afternoon in this discussion. Please ask your question.
Okay, this is a very simple question regarding the theorem. You stated that you have a state on the C algebra, on the C star algebra, and then you map it to this Hilbert space. But
yeah.
This is for each state. You go to a particular.
Yeah.
How to connect this with the classical concept of quantum theory, where you have a quantum Hilbert space and the states are the unitary vectors in this Hilbert space?
Yeah, the problem is that that's very that's very nice in finite dimension. So because you have a theorem of von Neumann, which essentially tells you that all the representation are a unitary equivalent of the objects you care about. Okay, that's somehow. Let me make a remark. As far as I understand, the history goes as this. That is, of course, when you formalize this the first time, especially for Neumann formalization, you have an Hilbert space at the beginning, and you have. Okay, the algebra of observable are the self-adjoint elements in the Hilbert space.
Okay, yeah.
That was the initial point. Okay, but then people started to enter into problems, especially when dealing with quantum field theory, because then you can have inequivalent representation of the commutation relation. For example, Heisenberg commutation relation do not have a universal representation, and depend on the state what is the representation you're using. So that's this language has been developed after, and all essentially after people start to understand that there is a problem, and it's similar really. It's okay. So somehow there is no in full generality, especially when you have infinitely many degrees of freedom, you cannot fix. So you see usually there is so in finite dimension what will happen is that you have a state, and this state give you a representation, and somehow all the other states have representation which are unitarily equivalent, or all the other interesting states. Okay, and then that means okay, let's just fix this representation, and because anything can be done in this representation, any state can be written in this representation. Okay, all the Hilbert space are unitary equivalent. So you just fix one and then you transport everything in this Hilbert space. That's what happens. That's what you are mentioning. Now, in infinite dimension, you don't know what is the Hilbert space because different states can have inequivalent representation. So you cannot put the representation in relation one to each other. That's also happen in it's related and happen in probability theory. Okay, when you go infinite, so all the finite dimensional Gaussian, for example, have measures which are absolutely continuous with respect to one of each other. So you just use the Lebesgue measure and you work there. Okay, and you write all the Gaussian with the density on this Lebesgue measure. But in infinite dimension, I mean, Gaussian have very different supports. Okay, so you cannot write any Gaussian as a density with respect to another Gaussian.
Yeah, of course.
Yeah, that's a problem in infinite dimension. So this language has been developed. What I find interesting and what I understood it has been developed by essentially by Siegel and other people. So sister algebra were introduced in this context by Siegel. He was pushing to because you have this problem of representation. So you want to commit to a specific representation only as late as possible, because you don't know what is the one which is pertinent to your problem. And all the problem I will talk about, that is these infinities, essentially are related to the fact that you try to construct a representation from another representation which is too different. Okay, it's
thank
vague,
you. Yeah.
but that's the idea. Okay, that's so can the issue of unbounded observable with dealt with resolvent? Yeah, so I think that's somehow what you say. You don't use resolvent. So what we are going to do is, you see, what you do in probability theory, in probability theory, when you do the general theory, you always pick a bounded random variable. Why? Because otherwise you have problem with integrability, okay? So of course you have Gaussian, but when you define the Gaussian measure, you integrate only bounded function of the Gaussians, for example. You see, and here is the same. That of course you can use the resolvent. The resolvent is a very specific bounded function, which has nice algebraic property, but there is no reason why you have to take the resolvent. You can take any function of A bounded, and this gives you a bounded observable. I will mention this later, okay? Because we will have to deal with things like that. So let me close for this morning at this point, and I think we continue in the afternoon at 2. I will maybe, you can have more answer. So see you later. I stop recording.